In this video, we're going to use our time-dependent perturbation theory to look at sinusoidal perturbations in our potential. And we'll see in the next video that the reason that we are interested in this is because that is how we can model electromagnetic radiation. And so when we want to think about sort of the absorption and emission of light, then we will want to use this sinusoidal perturbation of our potential. All right, so if the perturbation of the potential has sinusoidal time dependence, then we will end up with this right here. So our potential times this cosine here of omega times time, such that the off-diagonal first order perturbation here is going to be equal to this. So this is the off-diagonal part of the potential here, which is what we get because this is the sinusoidal pattern here. And so we are defining this V of AB as, like I said, the off-diagonal elements of this matrix here. And so we have this right here for our first order correction to the probability amplitude right here. And so we put the cosine here into our integral, and then we have this VAB here. Well, we can use the trig identity for this cosine here. So this trig identity of putting it in terms of these two exponentials here. So we can then sort of turn it into this right here. Then we do some rearranging, sort of taking this 2 out of here and distributing this into the parentheses there, and so we end up with this right here at the end. So then we want to evaluate this integral, and so when we do that we end up with this right here. Well, we're assuming that the transition frequency here and the driving frequency omega are very close to each other, since other frequencies would be much less likely to cause transitions, which actually we'll see here at the end of the video why that is the case. But we know that the driving frequencies, so the frequencies that are going to cause these transitions, have to be close to this transition frequency in order for a transition to occur. And so we're saying that this omega sub naught plus omega is much greater than the difference between them. And so what that means is that this term right here will go to 0. So we will have that go to 0. And so we can just sort of cross that off there. And so we end up with this right here. We do a little bit of manipulation here. So we're going to factor out the sort of square root of this here. So that's where this over 2 comes in here. And so we have this t over 2 here. And so this times this first term here would just give us this again. This right here times the negative of that would just give us the 1. So that's where that 1 comes from. Then we use the trig identity that the sine of x is equal to these exponential terms right here. And so this has this I in the middle, so we'd have to bring that I out front here. And so that's what we're doing right here. We bring the I out of there and do some rearranging. And so we end up with this right here. And this tells us the probability that the particle in state psi sub a at time 0 will be in state psi sub b at time t. So it tells us the probability of a transition in the time between 0 and whatever time we are at in the future. And so we are looking at the probability, so we have to square it, so that using the Born rule. So we're squaring this, we're squaring this. So when we square these imaginary terms, what we're doing is multiplying it by its complex conjugate. So we get this, which will just be equal to 1. We are squaring this here, so which will also be equal to 1, the square of negative I. And so we end up with this right here. We do some rearranging, and we end up with this right here, where this part here is going to be a constant, and then this is the time dependence right here. And so this is the amplitude here. I don't know what's going on with that, but this is the amplitude of our sine squared wave here, and this is the sinusoidal function of time, which tells us that the probability of a transition oscillates sinusoidally in time, and this is called the Rabi cycle. And so at times t equals this n2 pi over this omega sub naught minus omega, the probability is 0, and then at n minus 1/2 here, the probability is the highest, though it'll still be a lot less than 1. And so that will look like this. So we have our probability on the y-axis, where the maximum will be this right here, the amplitude. And then we can see here at these times that we have the probability of 0, where right here the probability is equal to this right here. And so the probability of transitioning is actually oscillating in time. So depending what time you make your measurement, you're going to have a different probability of seeing it in the transition state, seeing it. So if we're starting in state psi sub A, then the probability of detecting it in state psi sub B will oscillate in time. So there will be different probabilities at different times. And so if we look at this as a function of omega, what we see is this. So this is the transition probability as a function of the driving frequency for the sinusoidal perturbation. And so what we see here is that this is sort of centered around this omega sub naught here, which is why we could make that assumption that the omegas are going to be close to omega sub naught, because the probability of a transition is dependent on the omega being close to this omega sub naught. And so the peak height of this potential term here times t over 2h bar squared. So the width of it is 4 pi over t. And so we see that this depends on t, and so that will narrow with time. So this will sort of keep narrowing inward as time goes on. So though the perturbation assumption that we're using only allows for short time spans, so this theoretically sort of keep going infinitely until you get sort of, like a delta function here right at omega sub naught. But this perturbation assumption only allows for relatively short time spans. And even if we didn't allow that, it would never exceed 1. So this probability here would never go above 1, because you can't have a probability greater than 1. So what this tells us is that the frequency needed to cause a transition must be close to the transition frequency omega sub naught, that the frequency needed to make the transition narrows as time goes on. So the driving frequency needs to get closer and closer to this transition frequency. But yeah, that was everything I wanted to talk about for this video. So looking at a sinusoidal perturbation to our potential term. The next video we will see this being able to be used for calculating the absorption and emission and stimulated emission of photons from, say, an electron in an atom. But anyway, I hope you found this video helpful, and I will see you in the next one.